Hello everyone. Welcome to my channel. This is the seventh day of solving Leetcode problems, and I'll be solving the problems live. And I haven't read this problem before, so we will be building the approach from scratch. And here is the today's problem: maximum number of moves in a grid. And the steps are like this. So we will first read the problem, and then we will see the examples. We will try to build a logic that fits to solve this problem, and then we then try to check, give it the algorithmic touch. Then we think about complexities and whether it satisfies the constraints or not. And finally, we will make a submission to check if it is a correct solution. So before starting, I'll check if I'm currently live or not. Hello everyone. Welcome to my channel. This is the steps. We will try to build a logic that give it the algorithmic. Okay, perfect. We are live. So let me just close this and I'll expand my notepad. All right. So this is your question. And let me know, guys, if you hear any kind of background noise because currently some festive season is going, so outside environment is not that good. Okay, here we have this. The question of the day is a maximum number of moves in a grid. So we are given a grid and we have to find maximum number of moves. Now, what are these moves? Let's find out. So you are given a zero indexed m cross n matrix. So the matrix is m cross n, consisting of positive integers. Okay, so it's n cross n matrix and it has positive integers, right? You can start at any cell in the first column of the matrix and traverse the grid in the following way. So you can start at any cell in the first column of the matrix. So let's say this is our matrix, and here we can start from any cell in the first column of the matrix. So this is the first column. So we can start from any of these cells and traverse the grid in the following way. From a cell row, comma call, you can move to any of the cells, this one, and this one. Let's get an idea of that. So let's say we are at this r comma c. We can go r minus 1. R minus 1 means this particular row, right? And call plus 1 means this particular column, right? This particular column is call plus 1. So we can go here, sorry. So we can go in this row and in this column. So we can go here from this particular cell, right? And we can go row, comma, call plus 1. So row is in the same row, right? And you can go to this particular point. So this is call plus 1, right? And you can go row plus 1, call plus 1. So row plus 1 is this row, and call plus 1 is definitely this column only. So we can go to this place, right? So guys, the movement is like this, right? We from a particular cell, we can go to these cells. So this is your basically a move, okay? So you have to start from these particular cells. Wait, let me mark it with some other color. Let's say these cells are the starting point. Any of these. So basically, you can choose any one of them to start with, and then you can just travel like that. Now, there's one more condition. So you can travel to these locations such that the value of cell you move to should be strictly bigger than the value of the current cell. Okay. So here is a catch. If you are at some particular cell and it have some value like val, and you can go to these three cells, right? But you can go visit them only if their value is greater than, I'll call val2 is greater than val1. But val1 is basically this. So this is the condition. So you have to return the maximum number of moves that you can perform. Okay. Maximum number of moves. what is done? So this, if they call this as a move, because it is not mentioned here. This is the way of traversal. Now, what is a move? Uh, Maximum number of moves. I guess if it is not mentioned, then this particular thing will be the move only, right? This will be counted as one move. All right. Or let's see the examples. They will help us build the clear logic. So we have been given this matrix. First thing first, we can start with rows in this particular column. So this is the given matrix. Okay. And the output is 3. Let's see how. We can start at the cell 0, 0. Why? Because it's the first column cell, and make the following moves: 0, 0 to 0, 1 here, and 4 is greater than 2, and 9 is greater than 4. So here we have three options, these three places. So this place is invalid, this place is valid, but this is lesser than this, so it makes it invalid, and this is valid place, but it is also greater than 4, so it is a very much valid place. From here also we can go to these three locations, and since because of 9 these two places are invalid because the value of these cells is lesser than 9. In this cell it is 11 and it is also a valid path. So this is a good basically this is a good traversal, right? So okay, so this is like you can make these three moves, one, two, three. It can be shown that it is the maximum number of moves that can be made. So they say the answer is 3 because of these three particular moves. This was the first move, this was the second move, and this was the third move. So basically they want to traverse till the end. Maybe that's what a move constitutes. Find the max, return the maximum number of moves that you can perform in. Acha. So I think it's like the maximum number of moves you can perform in continuation, right? That's what they want to ask. You can obviously perform more moves. Wait, let me check here. So like from other cells, we cannot really move, right? No, so no, from 3 we can move. So let me just erase it and try it from 3. And what is the answer we get if we do it via 3? So let's say if we started with 3, because 3 is a valid cell, which is in the first column of the matrix. And from 3, we can go to these three locations, and all of these three are valid ones. And from this 4, we can go to these three locations. And this 4, we can also go to these three locations. And from 9, if you like, let's take this simple example. If you come to 9, you can come to 11. Right. So this is the valid path again. We got one more valid path, but the path value does not change. It is still, it is 3 only, 1, 2, and 3. So 3 is the max thing which they hit already. So in that case, no matter whatever we try to find out, it will be less than 3 only, because if even if it's a straight path, so it will perform only 3 moves. So what I deduced from this is basically a move is basically a maximum, by maximum number of moves, what they mean is if you try to progress consecutively. So clearly this is not mentioned in the question, like what a move is theoretically in general, right? But yeah, obviously what we got from example is that you start from the starting point, and whatever trajectory you get with some path, the length of it is the length of it will basically determine the number of moves. So if the length is 1, 2, 3, there are three moves. Basically, we made three moves to create this. Basically, you create all the valid paths which you can traverse, and out of which the one which one is like whichever is the largest one is your the answer. Basically, you made maximum moves in that trajectory. So here it's basically the question is, out of all possible trajectories, which one has maximum number of moves? That should be a clear statement, I would say. Now let's take another example and verify our logic in a better way. So we will do it without looking at the explanation here. So starting points are these three. So first let's do with 3. So from 3 we can go to these three locations. This is invalid. This is also invalid because it is less than 3, and this is also less than 3. So by 3 we cannot even move to one step. So it's like till we have got 0 Like the current number of nodes we have performed is 0. From 2, so yeah, this is basically a edge case only. So this 2, we can go to these 3 locations, and since all of these are less than or equal to, since this is not strictly greater than, so that is the lingo you should guys, you should basically guys, you should notice here, it's strictly bigger than the value of the current cell. So for 2, if you have 2 over here, the next element should be 3, 4, like that, not even 2. Here also we got no valid location. And if we just try to do with 1, again that's the same case. So sorry, 1 for 1, these are the valid paths. Out of which you got nothing. Right, so guys, what I noticed here while doing these examples, it might be that you did not notice, is basically that there is a lot of repeated computations involved here. See this? When I was let me draw this. When I was traversing this cell, uh, you can go to these 3 locations. After you come to a valid location, so this is an entire different problem. So now your starting point is this, and you will progress to this direction, right? So for 3, you solve a similar problem here. Like you go to these 3 locations, and then you come to a new cell. Here also it's a different space. Basically, you calculate for this part, and this calculation will never change, right? For this particular cell, if you do calculation once here, and when you come back to the cell, somehow this calculation will remain same, because you will examine these 3 nodes and you'll go to these nodes, and then you try to basically move to a valid node, and then you continue the same thing, right? So what I get here is, let's say if you consider this node, right? For this node, again you have to do computations on this value, and then you have to do computations on this value, then you have to do computations on this value. Now if you try to compute for this, again you are doing a repeated calculation, because you have already computed this node when you were at this place, right? Because it was the second step of that process. So somehow, if we remember what was the result of this, what was the path that you constructed by following this, you can directly use that at this place and return it like this. So if you're doing it for 2, so the answer will be, so 2 going from 2 to this cell will take 1 move if it's a valid move. And then whatever the answer of this particular thing is, we will just take that here, right? So essentially this is a DP approach, right? You will be just traversing, visiting some nodes, and you just cache the calculations of them when you have done it once, right? And doing that will basically help you to do the computations in order m into n. Again, this is not how we move, but this is my intuition at the moment, right? Now I'll just talk about how can we solve this problem in a brute force way. So for brute force way, guys, what we got is this. So we got this. We just take 3 first, and then we will take 2 at the next step and 1 at the next step. So we will start with 3. This will be our starting point. And after that, we explore the options for 3. Let's say we landed to 7. Let's say this is 7, right? So then you will do this. You'll continue this branch, and you'll try to calculate everything here. And this will be basically, so in the worst case, so let's not talk about hyperplicity. So from 7, you go to the next steps, and then again you continue this process, and at the end, when you are ending it at the last cell, you'll just report whatever the length of path which you have traversed previously, and you just keep track of what was the length of the paths which you have traversed earlier, right? So this is the approach for brute force. You do it for each and every cell, and That's the thing. Now this is pretty much simple. I'll just write it again. So this is the algorithm for brute force. And those who don't know what brute force is basically the uh, solution which considers all the possibilities of a problem. Basically, all the paths you can think about that problem, all of them will be considered, and you will get the answer at the end with that. And here, first step will be for each cell in first column. Sorry. So for each, you will do this computation here. I'll call this compute. What will you compute? This compute will give maximum moves from that cell, right? And at the end, what will you take? So let's say for each cell, we calculate this compute value, and at the end, we do the max of all compute results from every cell. That would be your maximum move overall, right? And this compute is also simple. So what will you do in a compute function? Compute is basically a recursive function. Let's say you started with 0 comma 0, then you will just write what are the next states, what are the next rows and column pairs you will be traversing, and that you can easily get from here. These three things, and I'll just write it. I write them down. So basically, this will be all of them have j as j is increased for all of them, and rows are kind of different. They're in different way. This is an invalid cell. You just don't need to worry about it. Now you come to these two cells. Now you will do what? You will process this path. You'll compute for this. So this is where recursion is going on, guys. So you have this particular starting point. You have this as next point. So you'll compute for this path. What is ahead of this path? And you will just compute its result, add in 1 to it because you are making one move already to move to this stage. Now you do this. You do for this as well, this particular path as well. It will be 1 plus compute 1 1. So this will be 0 1. Now you follow this compute, right? You will do the next compute for this. First, you will get done with this part, then you will get done with this part recursively, and then you take max of these things, which will be the answer of the current compute, which is compute 0 0, and that is for the zeroth cell, right? The same thing you will do for the next compute, which is essentially 0 1. So you see what is the condition, right? Now this is the algorithm, right? Everyone should have gotten this. This is a brute force algorithm where we are trying to solve this recursively. So brute force considers all the possibilities of all the paths which are possible, and here it is doing that with the help of recursion, right? Now let's check at the constraints which we have. So m and n could go up to 10 to the power 3, but there's one more thing here, is that m into n will not exceed 10 to the power 5. So if you multiply these, you'll get 10 to the power 6, but that's not true. M into n value is 10 to the power 5 only, and the value of elements in grid lies from 1 to 10 to the power 6. So value is, I don't think, a concern because we have to just compare the two values, right? So if you follow this approach, guys, so let me draw the time complexity graph for this. So every recursion problem has basically a stack, basically a set of steps which you take, a set of options you get, right? So this is, let's say, the starting point, and from starting point we have the number of rows we have, right? So we have these, the starting cells as the starting point. So how many starting points we have? We have r. R is the number of rows, so r starting points, right? So this can go up to order of, this is, can go not, this is basically order of n here, and you get these states here, and from each state you can go to three different states, right? And then you'll come to the second level. So by this you just, the depth of this tree will be m. Why? Because you move to the other state, then you move to the other state, basically you are going in forward direction, so the depth will be m, and at each step we have, so here we have n nodes, and here they will get each will get basically, this would be I would say like 3 3 3 3 3, so it will be 3 in here. In the next step it will be 9n, like that it will go till m, right? So it will be basically 27 here, so it is basically 3 to the power m times n at the end, and you have to, yeah, basically there will be this much leaf nodes at the end. If you check the complexity of this can go up to this. So, which is a very much bad solution, guys, because if you square this, it will be 9, and we just do this 2 multiplied with 500. I hope this is right. I'm really not sure about this because it's really 10 a.m., guys, and I'm exhausted as hell because I worked a lot today. So this is basically your you can round it up to 10. So this is 10 to the power 500, and we, what is acceptable thing is basically 10 to the power 7, or at worst you can examine a 10 to the power 8 solution if it can pass by some hiccups in the late code itself. So best is to come with below this, and if you get till this, it's fine. So obviously this approach, this recursive approach, is not a good fit for this. So what it is, so I actually told you earlier, because these computations are repetitive, we can actually cache them. So it's a very much simple DB problem, it seems. So let's come and construct that logic, and then we will jump to the code. So guys, this is the thing. What I'll do here, I'll just make a DP of a particular cell's result is fixed. It won't change. If you start from this particular 4 cell, you will get this path, right? And what this path has the length, it has a length of 2 step, right? You made 2 moves for this cell. So after this cell, you made 2 moves, which is the maximum number of moves you can go, right? And from this cell, if you try to do, you will go to 4, then you'll go to the same path, right? So when you are at here, you are doing computing for 4, then you will be at 5, and let's say it was 2, you'll do compute the same thing for this 4 again, because this is an independent node, right? So basically what I was telling here is basically you can have DP defined as for each cell. So if we have RC, this will uniquely identify a particular cell in this grid. Any cell can be defined with this notation and it will be unique. So this will denote the maximum moves from that location towards right, this way. And right, this is the thing. And you, when you are, so this will be done basically. And now when you compute them and you just cache it. And when you do it for this particular cell, this particular cell, let's say it was 2, it was never 5, let's say it was 2 or some 3. So for 3, what will you do for this path? Just directly use this for this path. It is directly use this 2 result here, and you just do 1 plus 2. So you will report the answer of 3. Then for this particular path, the answer is 3. So these paths you need to explore again. But again, for this path, you can just use how you did. Do you get 3? You get it by 1 plus 2. So guys, this is the power of computation caching, which is known as dynamic programming, and which reduces the complexity by a lot folds, right? Let me just show you how it reduces the complexities. So again, here also we'll have n starting points. But after this is the interesting thing. You will go to these nodes, sorry, not that, these two nodes, and you cache the result. You go ahead, you progress this entire end, and when you come back, you keep caching them. So basically, each node is traversed only once. So the no node will be visited like even not no node will be explored even twice in this particular approach. So let's say for example, let's understand this like this. So let's understand. So for 2, if you explored 4 here, you explored this path. Now when you come with okay, so guys, let me just change it to 2, which will help me explain better. Now when you come to this 2, and when you hit this point, you will just use the cached value over here, which is dp 0. 0 means this particular row, and 1 means this particular index. So since you have already calculated while traversing with 2, this is an order 1 operation. So here for 2, you explore this path in order 1 time, while it could take order n, because we might need to go to these particular nodes from here. Yeah, you get this. So basically for each node, you can basically spend 3 computations only. So at worst, this can go in this order. So this is order n into m solution when you use caching. Now, let me define the approach. How will you do this? So we will define a DP thing. DP, first step is define a DP array, which will store these values. So when the nodes are not computed, we assign these to -1. You assign these to -1. Then what you do, you prepare a compute function. This compute function will take rows and columns and obviously all other stuff to maintain the data structure, which we will discuss in the solution, but these are the main things. And it will also take the grid, and which is in here, so I'm not writing it. So compute will have rows and columns, and it will compute for that particular row. And compute logic is different. Compute logic is basically the DP logic, basically the recursive logic. At the end, we cache the result, right? So this compute function will have to be defined. Third step is to answer is basically max of all the computes, all the computes yeah, all the computes r2 r2 c1, all the computes for this particular these all these cells, and that is your max number of nodes if you follow the constraints, right? So this is the small DP logic here, right? And if I talk about recursive logic, so basically you will be starting from this point and you'll be moving progressively towards the end. So basically from each state there are 3 options, And if you explore a non-existing node, basically, which is basically negative indices, like if you try to create those three indices for this particular index, you will end up creating this one, and this one. So this is an non-existent index. So the base case, in the base case, we will handle the negative indices and end path. So basically, if we arrive to the end of the matrix, we cannot go ahead. So from here, obviously, there is zero moves possible from beyond this point. So you should always keep in mind the meaning of DP, which is very much important when you solve a DP problem, right? This should be in your mind while you're coding up, then you will not mess up, right? So here is the base case, negative indices end path. So negative indices and end path. So negative, for negative indices, we return zero because obviously there is no possibility from that point. And in fact, we don't even try to push negative indices, or basically, if you do this like 1 plus, and you do this compute with a negative index, so you actually need to return -1 to nullify this particular move. Because by adding 1, we assume that from this node, we have already progressed to this particular node. When you return -1, it means like there is no path possible here. And there's one more edge case, base case, which is basically cell value less than previous. So this is not this is also an edge case because this will if we have this values, like if the value is already less, we will not explore further, right? So let me just erase the unnecessary stuff. Wait. Yeah, so this is our so delete these. So you just need to keep in mind this DP logic here in this particular flow, right? And now we can move to the coding, and where we will be building the solution, right? And this solution is obviously order n into m, which passes these constraints because n into m is of the order 10 to the power 5, which is well under this condition, this thing, the time complexity limit, right? And yeah, so we will be coding this up. Okay, so I'll check if someone is actually with me or not. Um, Guys, don't mind my recommendations. Someone is actually with me or not. Yeah, so we are actually live. And okay, so let's move to the code. Hmm. Thing first, what we need to define, like we do in all the problems, is the data structures. So I'll be needing M and N. So M is basically grid, number of rows in the grid, which will be grid dot size. Not a rocket science, guys. This is very much easy to define. And here you need to take a caution here because it can be there like the grid is empty. For that you need to check the constraints. So yeah, so M and N are basically at least two. So we can take here grid zero dot size, which will give us the number of columns in a particular. And then you need the DP data structure, which will be a vector of n, because it was a 2D vector, as you can see over here. It's it's a 2D vector, right? So it can go up to maximum to the index of a particular row and the index of a particular column. Here I define this and I'll also assign the values to this. I hope I can do it like this. So first what I do is basically call this vector as dp, and then I assign it here only in this line of code, in which I can do it by defining the size of this dp. So there will be m rows, and there will be a vector at all the rows, which will be initialized with, which will have a size of n, and it will be initialized with -1. -1 means the dp is not computed yet, right? Pretty much simple. This is the thing. Now, DPs can be solved with two approaches. The first approach is uh, recursive approach, which is very much easy to implement, and it feels like you're solving it. And if you use the iterative way, which kind of assumes that you already understand how DP is flowing. For beginners, like people prefer using the recursive approach. For iterative thing, even I have not done much in that. But if you guys want, you can just comment, and after solving it recursively, I'll try to solve it iteratively. And we can also, like, I'm also learning, you will also learn how you approach things iteratively. Okay, so let's build the DP recursive logic, right? So what we had here, so we assume we define a compute function. So we assumed that, so we will now define that. So that compute function returns the, what does it return? It will return this exact thing, maximum moves that you can get from a location when you move toward right, right? So I'll call this compute only, and I'll have, this is I is the index of the row, and j is the index of the column, and you need the grid. So I'll just copy this. Basically, it's kind of long thing to type. So I pass the grid, and here I'm using ampersand. This is very important, guys. Otherwise, you had to declare this globally. And when you are using ampersand, it means you're passing this grid to the recursion stack by its location. You're not actually copying this grid. If you don't do it, you'll get a DLE, because pushing to the recursion stack will itself copy this, which is an order n operation. And if you did not understand what I just said, you can just make a thumb rule that when you pass variables, you just use an, when you pass data structures to the recursive function, use an ampersand. And same goes for our dp dp array. It is also a multi-dimensional, a two-dimensional vector, as you can see over here. And I have used an ampersand. Now I'll just start writing. So recursion has this particular format. First, you basically DP has this particular format. Here, or recursion also. Here is your base case, and here is your caching logic. Caching logic will hit after the base case, and then you just explore the next stages, save the result to the cache, and return. Basically, this is the format of a particular DP solution, which is recursive. Now, so let's assume that we have completed this function, and as per the promise, it returns this thing. Maximum moves from a particular location, whatever we feed R and C in that rows and column index to that, it will return the answer from that point. So let's say if we feed 9, it will return from 9 what is the maximum number of moves you can make, right? So what we have to return? We have to return maximum number of moves that we can perform through all these possibilities. So what we will do, we will push each one of them one by one, and whoever gives us maximum thing is our answer, right? So I maintain an answer, a variable here, which is initially set to 0, because we haven't explored any particular path, right? So the number of moves we have done is 0. Now I'll just do this. I'll traverse in the first column. So when you traverse in the first column, basically you access all the rows, right? How many rows we have? So I'll make an iterator, and it will iterate all the rows. So we have m rows, and this will iterate those m rows, and we will now update our answer with max. We are using max because the better we get, we update answer with that. So this is the existing value of answer. Now we run a compute function on this, which will be basically passing the I and j here. So I and j are indices in the matrix. So here I will be the same, which we are having an iterator, like, and then we pass the j here, which is 0, which will ensure that what we are passing the first index of each row, which was first index of each first column, like each index of first column. So this will ensure that we considered all the elements in the first column, right? So this is your answer, and then uh, if compute works well, you just return the answer. Now, come to this point here. If here also we need the number of rows and columns in order to check the boundary conditions, right? So this is not the base case. Uh, Instead of getting the size again, what can I do here is basically wait. So here I forgot to pass some values here. So I'll pass the grid here, then I pass the DT here. Apart from that, I also pass M and N to be used here. Right? So I'll just declare M and N in the function. A single values you don't need to really care because they are just you don't need to pass it by the reference to reduce things because they're also there's already a one, right? Now let's do this. What is the base case? There's one thing I would like to tell you. So this negative indices, we try to not explore this path beforehand only. So don't worry about this. We'll consider this like we will never push negative indices to our compute function. So and also this one like cell value. If cell value is already less, why will we try to follow that path? So we'll never push these two cases to the compute function. So they are out of base case now. Now we just need to check the end path. So if it at the end you return 0, right? Because if you are already at the end, there are no moves possible beyond that point. Okay, so enough talking. I think I explained a lot in this case. Oh, okay, so here I'll just go ahead and check that. So I'll check if the cell which I'm getting, not the cell, if the I which I'm getting is beyond the limits, which is basically I is greater than or equal to m. Since I is zero indexed, so we need to check if it is equal to m also. If it is equal to m, then it's already beyond the limits. Right, and not and basically either of these conditions, if it is true, it means that we are traversing a faulty path, we have a faulty cell basically. So if j is greater than equal to n, that means we are at this particular outside 5, we are at this particular column which is not existing, right? In that case, we just return. Okay, so earlier I told you like I won't be considering this case at the first place. So we just need to check here if we are at the end of this particular thing. So for if we are at the end of this particular thing, for that what I need to do is basically just check if the value of the column is end or not. So for that I'll just do this. So j refers to the column number. If j is equal to the end, which is n minus 1, means we are at the last point. And if we came to this point, it means that we already were at the valid path. So we return 0 because beyond this point, there is no path possible. Now we have the caching logic. Caching logic will basically check if DP has been cached or not. So I'll just add ij here, and if it is equal to, if it is not equal to -1, it means that it has been cached, and in that case, we return the dpij, which is the cached value. Makes sense? Now next is so here we will consider these two cases as well: negative indices and cell value less than the current value. Okay. So guys, there is a good technique which I would encourage everyone to follow when you are doing these kind of grid pathways which basically change when you have to travel across a grid, across a graph, something like that. For grids, this is the popular way of doing it, and it's quite handy. So you define dx and you define dy. Now you'll understand what these are. So basically, see here. So we are at r comma c, and we need to travel these cells, right? So you write what operations, what dx means delta x, what by what amount you are changing a particular row in a sequential manner. So let's write for dx. So for dx, for this particular transformation, I am making minus one over here. So I'm making the delta is actually minus one here. In the next one, the row is as it is. The next one it is zero, and in the next one it is row plus one, which is plus one, and plus one is like just simple one. And dy, note this, dy should be corresponding to this only. So this particular, the first element should be for this particular transformation. Here we are adding one to the column, so we write one here. Now for the second one, we are also adding one to that right here, and we are also adding one to the third one. So it is all one, one, one. This is a popular practice for what? When you try to explore the next stages, you don't need to do it one by one. You don't need to make this variables to do these things, right? You can just iterate in this particular array. So this is an array which I have made, and you access the zeroth index of both to make this transformation, first index to make this transformation, and second index to make this transformation. So it will be clear when I prove this. So now, if I have to explain the next stages, I'll do this. So I'll iterate. I'll have an iterator which runs three times. So let me just do it like this. So here I have to also return the answer of the state, which is zero at the moment, right? Now I'll do a loop for three times, and right, I'll do this then. Okay, so I need the indexes as well in the. So what I do, I make a for loop. So basically, I was doing while because we were already using I and j is here, right? Let's use other variable k 0, k is less than 3, k plus plus, and now k equals to 0 will give you k equals to 0 give you this index, the first index of dx and dy. So new row is basically current row, which is I plus dx of 0. New column is basically I plus dy 0. So guys, you see, like earlier you have to do this for all the three cases in different variables. Now you just run a loop, and it's very much simplified for each and every test, each and every case, each and every stage which is possible from this particular point. Now you add these conditions. If it is a negative index, or if it is a cell value, if its cell value is less than that. Okay, so we do that. So for negative basic check, I'll do this. NR is less than 0. Since we are subtracting in case of x only, we really need to check about this one, right? And there is one more condition here. And another condition is that if the value of grid at that particular new row and new column, so now notice this. This can this cannot, even if we are adding one here, this cannot go out of bound. Why? Because if it was the last index, at the first place only we have tackled it. So whatever passes below this, it is basically one step before, at worst one step before the last index already. So we can clearly check and see here. Otherwise, we might need it to add a condition for NC here as well. But now I guess it is fine here. So we assign this to so we check here, not assign. We check here if it is lesser than the current value of the particular cell which we are at, right? So here I had a mistake. It should be J. Right. So now, what I need to do if we encounter a case which is like not possible to explore ahead, we just make a continuous statement. Continue means like you would skip this particular step and you just move to the next one. Now, if it is a valid step, what will you do? You'll update your answer with the similar settings with better answer here. Now you can take one step, and where are you going after this step? You're going at this step where your I and J's are this, and obviously the other stuff you need to pass on as it were earlier. So now if you didn't use this for loop, right, using this thing, you had to write it for all the three things, and it would just expand like 20 lines or 15 lines or something. So this is what it makes it clean and easier to understand as well. You get an updated answer after this step, and now you save it to cache and return it as well. So you just save it to the TP, which is IJ has been traversed, and we got this as answer. Right. Yeah, this is the entire approach for the recursive DP. Let's run it. There might be some errors, but we will try to fix it. Yeah. So this is access elements. Oh, sorry. Basically, I forgot to add an array here because dx and dy is where arrays. If I run this again, um, okay, so maybe I need to define size. I'm really not sure what syntax is because I'm starting this after 2 months, maybe. Okay, so I'm returning things. I'm not progressing. Okay, so I made this mistake here. It should be K, right? We got the same error again. So 0, 1, 2, dx, dy. What is the error? Addition of unsigned offset. Um, First, let's find out where the error is, right? Wait, we have IJ grids. Do you guys spot any kind of error? You can just write in the chat. It will make our effort easier, right? Now here is this thing. Basically, let me think where the error is. If I'm not getting it, first thing which I'll do is to check the entire logic once because it will help us to verify the hiccups at the first place. If we go blindly and print statements, that's not a good approach. So here we have the grid sizes defined here, correct? And then we have this DP defined here, which is of size M rows, right? And there are n columns each. Each has been given -1. Then you have answer, and you now iterate for all the rows, and you pass this I and J is the 0 here. The first column element for each row. And then you have this answer as max of answer and this part. So here we have I0 grid dp mm, and here we have ij grid dp mm. Here's the base case, j equals to n-1, return 0 because we are at the end of the column. Perfect. We cannot go any further step from there. Then we have the caching logic. If it is not equal to -1, return the dp itself. Now do the processing for I say. Here we have answer and then you will just explore these three cases here, and these three cases are correct, I guess, because one is going in x direction up, same level down, and this is all the next column. So I think adding a plus over here will do the same thing here. And if we get somehow NR is less than 0, here we can get, let me think. Okay, when we add 1 to this, okay, got it. So there is this thing here I did not consider. Basically, when you are here at a particular I rows index, you're moving up and you're moving down. So I just considered that this I is not negative, means I just consider the upper limit. What if I is and NR becomes greater than the number of rows we have? Basically, this NR can uh, exceed the number of rows we have in the first place, because we might end up adding one over here. So this was the correction which I identified just by reading the code, because our approach was already clear. Okay, then we ended up continuing it, and then you just make a max here, which is basically, so if we it's an invalid path, we also check like if the value is less, the value of the next row is less, then we don't need to explore this path. So we just continue to the next particular k, and now we are incorporating that to answer. Since it's already a valid path to the next element, we added one previously here, and then compute will give the answer for the next row onwards. That's the thing. And then we return the cast answer. So like this was the thing. If I just if I went to directly printing statements, maybe to getting this particular point, it would have taken me a lot to figure out. Right? I may need to end up add a print statement over here. Or if I'm not lucky, I won't even get that particular thing in the first go. There can still be problems, but okay. So the problem is something else, and now we have done this. Now we go ahead and print stuff. Okay, so the thing which I'm interested to print is basically ing over here, and the same ing over here with one thing here. I'll add a after here. That will just let me know like what happened with the particular thing. Okay, so we started with 0 0, and then we have 0 after 0. After that, this was hit probably, and so I still need to find out where is the error. I just have to paste it and check. Okay, I could have done here as well. I can do it now. Yeah, if it is with the arrays, guys, I'll be very much unhappy with that. No, it's not about arrays. Okay, so what's the problem here then? Okay, so it's with the arrays only. Basically, this step only. We were not able to move to the next step. Why? Okay, so addition of some offset. Hmm. We are returning an integer over here. Addition of unsigned offset to this overflow. Hmm. Can we have our NR and NC before this, please? And I'll also want to see the answer at this point, if I could get. So this is, guys, debugging stuff. It still not ensures like our solution is correct or wrong. So it went continuing it. So basically the problem is with these guys. Oh man. What I've done, this is the syntax of declaring an array. Mm-hmm. Oh, 3 means like, yeah, that's the correct thing. Declare an array in C++. That's what I'm doing here. I'm in there. Correct? What's the problem? Problem is basically k is also incrementing and k will go up to 2. I was not able to even get this particular value, right? This accessing is correct or not? Not really sure about that. Grid I, grid j, grid I, grid j. Okay, so we got -1 over here. Oh, sorry. This should be an OR. Mm-hmm. I really like ignored this thing. Basically, I had to check that. And I think this is the thing, man, which was the error. Yes. And now we have some different error, but yeah, you got that. Now we need to check about this particular test case. So this is correct. It is giving us correct answer. So here, what we got is this. We started from 0, 0, and then from 3, there was not a single place we could go later on, but we still went to 0, 1. And why is that? So -1 and 1 was skipped, right? Then we got 0, 1. 0, 1 was also skipped. And we got 1, 1 here, which was also skipped. And here we have this thing here after the 0 is computed. And then we go to 1, 0. Why 1, 0? We should go to basically 0, 1. Right? So okay, I is 1 here. It changes. Okay, so it should be 1, 0 only. Yes, correct. 1, 0. So 1, 0, and we come up with 1, 0, and 1, 0 was cached. 0 is printed, not cached. And then we have this. How did you get 2, man? Like, this is not possible. First place, they are not possible. Because 3, 2, 1 are the starting points. And this condition must hit. Let me just remove the other statements. Here I'll just print answer itself. And let me just remove these things. These are not making sense at all. Okay, so here is this thing. Now we started with 0, 0, and that has been computed. Got this 0 answer. Then we started with 1, 0. And what I am printing, man, like I have only 2 counts, right? In the entire code, I have 2 counts. Yes. So it means like from 1, 0, it went to 0, 1. How is that possible? 1, 0 is this 2, and let me just show you this example case. From 2, we cannot go to any further state because its value is just equal to that of, if it is less than this or equal to. I actually took that condition entirely and differently, basically. I don't know what I've basically I combined different logics to this statement, which led to this. Now it will pass for sure. I'm pretty much sure it will pass now. And yeah, basically it should be less than equal to, right? Because if it is 2 and if it is 2, in that case, this condition will be false. But if it we add an equal to, this will ensure that if the next stage element is even if it's equal to the that older state element, we should not proceed ahead. So yeah, guys, when you're coding things, you literally need to have the algorithmic meaning in your head. So let me just submit this. I hope we are done with the solution. Oh, I forgot to remove this. So here we are. We are okay. So we have solved it. So and this statement is kind of not important. Now, if any one of you are watching this stream, if you want me to code the iterative way of TP, just let me know. Just let me know in the comment. I'll start with that. And this is basically the solution. And we are printing some random stuff here. I know that this is not a part of solution, but this thing. So yeah, it is M to N approach only. If you check the complexity, I hope this works for this one. Yeah, it is M to N only. What I need to do next is basically I should remove that print statements, cout statements, and I don't think there are more. And this may beat more people. Let's try that, although I don't want to do that, but let's try. This lead code itself is a bit strange when it comes to calculations. Now you see, it beats 93% people who have solved this problem. Okay, so guys, this was a good problem, and we had this was basically, I would call it a straightforward problem. The ones we have solved previously were a bit tweaked, right? This was I got it in a I got it myself how to solve this, how to crack this part, because I spotted the computation thing, like recomputation thing, in the one go only. Let me check if any one of you want to
No problem. The ones we have solved previously.
solve this, the iterative part of this. So yeah, we got no viewers here. Fine. If you need, just put a comment here, not in the live chat. Maybe I'll premiere this. Put a comment in the comment section. I'll make a video for the iterative approach and post it here. So guys, this stream was today's. It was early because I was tired as hell, and now I will just sleep. If I could grab a coffee and so obviously I don't drink coffee, but yeah, if I kind of refresh myself, I'll do some other work. Yeah, so that is it from my side. If you have any kind of doubts regarding anything which we have done in this video, you can just put down in the comments and I'll answer them all. Okay, thank you. Take care. Bye.